the basic idea in topology mapping or virtual topologies is as follows. When you launch an MPI application, by default, the job launcher or whatever is the resource manager, that launches your processes 0 to n minus 1, ranks 0 to n minus 1. It will just typically put rank 0 on node 0 and rank 1 on 1. By node, I mean either core 0, core 1, or whatever is some logical ordering of 0 to n minus 1, because it doesn't know any better. So it just does a 0 to 0 and 1 to 1, and very simplistic mapping or launching of processes. That's okay, but if your application is such that the communication pattern is not from 0 to 1, by communication pattern I mean the majority of the communication, the bulk of the communication is not matching this 0 to 1 or 1 to 2 type. Let's say you have rank 0 communicating with rank 30 and 1 with 31 or something like that. That's not a good match for this default mapping of MPI ranks to cores or to nodes of the system. So, and that's because you're now communicating over a distance. And although some vendors might say that distance doesn't matter, so it does matter. If you're communicating among nearest neighbors, the performance is much better. So you want to avoid this long distance type of communication. So how would you do that? So there are two ways of doing it. One way is, suppose at the time of launching the application itself, if you could inform the job launcher or the MPI implementation that this is my communication pattern. Somehow you put that in a file or something and say, these are the processes that are communicating with each other. You launch the MPI application in a way that the communication is optimized. That is the nodes, the ranks that are communicating are located somehow close to each other. That's one way of doing it if the machine is able to do it that way. It turns out that it's not widely supported. It's not an easy problem to do the mapping either. So it tends to not be supported. There is another way of doing it, and that is what is known as rank reordering. That is, after you launch your MPI application with the default mapping, that is, when you launch it, you get the usual 0 to n minus 1 in COM-world that are launched on effectively 0 to n minus 1 number of cores. That doesn't change. But immediately after that, when you start your application, you can do a reordering of the ranks and get a new communicator that has a better mapping of ranks to cores. So there's a way to do that in MPI, and that's what we're going to cover, and that's called topology mapping or virtual topologies and so forth. So the rank reordering happens after the job is launched via some MPI functions. Is this clear what I'm saying? Maybe I'll show you an example, and then it'll get clear. So let's say you have an application that has, it's producing some kind of some scientific code, and let's say you run it on 8 ranks, and these are the 8 ranks, and this graph represents the communication between the ranks. It could be the number of messages, it could be the number of megabytes, whatever. So the number on the edge represents the amount of communication in some way. So you have this kind of communication pattern where 0 is communicating with 3. 0 and 1 are not directly communicating in this case. So if you launch the job with just 0 and 1 next to each other, it's not useful because they're not communicating. The communication is happening amongst other pairs of ranks. So if you just launched it in the naive way, I mean, if you just launched it without doing anything, then the job launcher would typically place on node 0, it would put rank 0 and 1. On node 1, it would put rank 2 and 3. On node 2, it would put 4 and 5. And then 3, it would put 6 and 7. Let's say they have 2 cores on each node, so that's why it's putting two MPI ranks on each node. So if you do that, and if you take this graph, it turns out that the amount of communication that is happening across nodes is given by this this number over here. So there's quite a bit of communication happening between nodes, and communication between nodes is more expensive than communication on a node. It's much faster if ranks within a node are communicating because they are shared memory communication. It's not going over the network and so forth. So instead, if you did a different mapping, and how do you do this different mapping is, I mean, what is the right mapping? That is also, it's a hard problem. It's like an NP complete problem, how to map a communication graph to a hardware node graph or a mapping such a way that the communication is minimized. That itself is a difficult problem, but there are tools that suggest an efficient mapping. So instead of this kind of mapping, you had a different mapping where 0 and 3 were on node 0, and then 1 and 2 were on node 1, then 5 and 6 on node 2, and 4 and 7 on node 3. This has much less inter-node communication for this application than the default mapping. So you have, just by the placement of processes, you have more efficient communication because it's the communication, more of the communication is happening within a node than across nodes. And this is just an example. So the question is, how do you get this mapping now, the one that will give you a better performance? So as I said, there could be two ways. One is at the job launch time itself, if you have that facility on the system to do this for you, you could get it. But that's typically not there. So you're not going to get it. You are going to get the default mapping. But you can call an MPI function, and we'll look at those functions. These are topology creation functions. What that will do is it will create a new communicator. So this original communicator remains. This is MPI COM world. This is what you got when you launched the job. And you had, this was rank 0 in COM world, 1 in COM world, and 2 in COM world, and so forth. That remains. By calling the function, you get a new communicator, a different communicator. You can call it whatever you want, the name, because it's just an output variable, in which the same processes have different ranks. So what was rank 0 in COM world is still rank 0 in the new one. That its rank didn't change. But what was 1 in COM world is now 3 in the new one. And similarly, what was 2 in COM world has a rank of 1 in the new communicator, and so forth. So from now on, if you don't use COM world at all, just leave it aside. It's there. You cannot get rid of COM world. It exists forever. But you don't use it anymore. You operate only with this new communicator and with this new set of ranks. Then for this application, which is what you were interested in, once you start communicating, your communication will be more efficient because there are fewer messages going across nodes and so forth. Is this clear about what I'm saying? So in this topology mapping stuff, the basic idea is what is important. The rest is detailed. They're just functions and how you use them and what they do. But I found in previous tutorials and so forth that people don't understand the basic. There's some confusion in this basic thing itself. Yeah. So it's better to yeah.
So how do you detect at runtime where the ranks are relative to each other? Which ones are close to each other? How do you?
In this case, you don't need to. We don't need to do that because. So what you need to know, what you do need to know, is the communication pattern in your application, in the logic of your application, and that you can know either by just knowing what the program does, or you can run your program once, instrument it so that you can, and there are tools for that also that can tell you what the communication is, who's communicating with whom. So you have that information. So it tells you because your program just deals with MPI ranks, it doesn't know the physical mapping. So assume that you know this. Once you feed that to the MPI topology function, and assuming that the implementation does a good job of knowing how to remap, because that's also not an easy problem. You give it the input communicator as MPI COM world, and you feed it this graph, and we'll see how to feed it that graph. It will give you a new communicator with just new ranks for the same processes in that new communicator. So a process in MPI can have many ranks. The one rank that is in COM world is what we call rank. Typically that's its main rank or something. That doesn't change. But you don't need to use COM world for your code. You can, once you've got the new communicator, you keep COM world aside and use this communicator as the communicator in your program. And so you now have, you just have different numbers for the same ranks. But because of your program's logic, your program is also not changed. You're running the same program. It's going to do the same communication. And it so happened that now 0 and 3 who need to communicate are located nearby and so forth. And yeah, go ahead.
So what happens to the data?
Yeah, good question. I was just about to get there. So you should do this before you get the data or something. So do this as the very first step in your program before you have gotten the data from anywhere, so that you can start with, once you start with, and you start with these ranks in the new communicator and then get the data either by generating the data or however you get the data, by reading it from a file or whatever, so that you don't have to do any remapping. So suppose you did this after getting the data, and the data was originally created with this numbers, ranks, you would need to move the data around, right? Because now that data was based on this numbering of 0, 1, 2, 3. So the zeros data would not move, it's the same, but the data that was 1 here would now have to be sent to this 1 here. There are different ranks. So that's why do this at very first before any data is generated, then there's no data problem, yeah.
At the very first of the program, how do I already know the communication intensity?
Yeah, so that's what I said earlier. You have to know it beforehand. So maybe you can tell just by the logic in your code because you're doing some kind of butterfly or some kind of communication pattern. You know that it's happening at some distances in your code. Or you can run the program once just to, maybe on a small scale or somewhere, just to measure the communication time. I mean, the pattern. And there are tools for that, or you can even do some small instrumentation to know who's sending to whom and what. So that's just a one-time cost to know what your pattern is. So that's how you know beforehand. So when you're running it in production or you're running it on big systems or whatever, you already know the pattern. Does that make sense?
In that case, can I just, when I launch, can I already give the mapping? I don't know.
Yeah, but that facility doesn't exist. I mean, on most systems, you will not be able to provide a file with, and they will not. That is a method, as I said, but it doesn't exist. That option usually is not available. Yeah.
You said that, but when you run in a small job, it's kind of different when you run a big ranks, right?
True. It might. So you might run in big ranks. You might run in a big case without actually sending any data, just sending the counts around or something. So you'll have to run it at some level where you get some understanding of what the pattern is. That may be just a dummy run. You're not actually sending real data. You might just be sending just logging the counts or something. So that I'm sending to rank 100 and I'm sending 1 megabyte or whatever. So is this clear? That what we are doing at the very first step, we are doing a remapping, getting new ranks in a new communicator, and then operating as if we have that new rank, ignoring the default rank of MPI COM world. So now just continue with, nothing changes in your program. It's the same thing, but it's better for this kind of mapping. Yeah?
What I still don't understand is even if you kind of create these new communicators, how can you be sure that the hardware is going to do what you want it to do?
That is true. So what is true, I mean, is that the MPI implementation, what might happen in practice is you give it this graph and you also even call the right function and everything. It is not able to do a good remapping for you because it's a hard problem and it's a algorithmically hard problem to find a good mapping. Some implementations may not even bother to do a reordering. You might even get the same ranks as before. your program will still run. It will not perform well as well as it could have because the implementation was not of a high, good enough quality, or it did not do a good job for you. But at least you did the right thing there. That you gave the implementation that opportunity to do it. So it's up to the machine. So the MPI implementation, at least in theory, knows the machine, knows the topology, knows the hardware, and it knows what should be a good placement of jobs. So this example is of like a common sense remappings that we are trying to minimize off-node communication. That's just one optimization. Even within a node, there is nowadays the nodes are so complex that even the placement within a node is tricky and important. So that's why it's not an easy problem. Not every implementation will do a good job, but many might, and at least on the commercial, the vendor systems, they should be able to do something at least so that you have a better placement. Yeah?
In the case of a program with a dynamic communication pattern, like an adaptive mesh, what are there facilities or is there support in some MPI implementations to sort of try to keep things local while also, while also giving you something that's a little bit better? Does that make sense?
So try to keep something local means by try to keep what local?
Oh, trying to minimize the data movement that would be required.
Yeah. So in those kinds of applications, the programmer is still doing the communication, right? MPI is just a tool for doing the communication. So whoever's writing that AMR code does the data movement or whatever. So the implementation will do what it is asked to do. It's not going to change anything underneath. So even here, implementation is not changing anything. It's doing what it's asked to do. It so happens that now the communication is happening among processes that are placed nearby from the beginning. Well, one option I think is that there could be some dynamic, halfway through the code, the processes could be moved around so that from then on, in a new communication pattern, this is better. But that's harder to do, and I don't know if anyone actually does that, or even a research platform does that. You'll also need to move the data around then if you do that. This one avoids the data thing because you're doing it the very first thing before generating the data or reading the data or whatever. Yeah?
So like we have, let's say, 16 processes on one node.
Yeah.
So who decides like which process is going to be rank 1, 0?
Yeah. So by default, it does a very simplistic mapping. It will do, 0 will go on whatever it thinks as rank or 0 or whatever. And by default, many OSs will move processes among the cores on the node. They don't even pin a process to a core. Because they are meant, like Linux, they are meant for more than MPI. They are meant for so many jobs, right? So they try to make best use of the system among all processes. But you can bypass all this. There are all MPage, OpenMPI. If you look at the advanced use, the job launcher manual, if you want to do something specific, it allows you to specify exactly which cores you want to launch the job, the processes on, and it allows you to pin the processes on the core. So once you launch rank 0 on this core, it will stay on that core. It's not going to migrate to the neighboring core and so forth. So those advanced features are available, but you have to manually do that stuff there.
So it is the OS which...
By default, it's the OS that on a single machine on a Linux, if you have a 16-core Linux box, the OS could move your processes within the box. It won't move it to another box, and it does that because that's how it manages processes anyway. There are so many processes when you look at the process table, right? And it's trying to make efficient use of resources when it's because it typically deals with an oversubscribed case. Right? But when we do parallel computing, we don't oversubscribe. We are running 8 cores, 8 processes, and for a long time. So we want them to stay there and have the ones that are communicating the most be close to each other. Yeah, there's a tool called HWLock, HWLOC, that the MPI implementations use to do this. And HWLock comes from France, one group in France, and that is just using other interfaces. There are interfaces available in Linux and elsewhere. So it makes use of those interfaces to map processes to cores and so forth. Any other thing? Because if you get this, then as I said, the rest is detail, and there are convenience functions and so forth. So, MPI has supports two types of process topologies. One is a Cartesian topology. So that is like a regular 2D or 3D or any number of D virtual grid of processes. So suppose you're working on a regular 2D or 3D mesh. How would you decompose it? And you would have sort of a virtual process layout, right? Where you would have the parts of that mesh divided among processes in all dimensions, and they'll be communicating typically among nearest neighbors, right? You do left, right, like in that life example, you'd be doing nearest neighbor communication among processes in a grid. So as such, there is no grid in the machine, but that's your virtual. If you draw a graph, it's just a square graph where the nearest neighbors are communicating. So that's a commonly used case. So there's a Cartesian topology to create that, and there are convenience functions provided to find out who are your neighbors because when you send, you have to actually give a process rank. So if you are somewhere, who is my neighbor, who's top down, left, right, and in the other dimension, that if you don't use these functions, you have to calculate that. There are convenience functions. And the other is a graph topology, which is completely general, like the one in the previous slide, where it's not a regular pattern of any kind. It's a general graph. How do you specify that, and how do you do that? And in MPI 3, a new set of collective functions, collective communication functions have been added that do communication among a neighborhood defined by a process topology. So suppose you need to do nearest neighbor communication, such as in that life example that we are working with. You could do the same thing as a neighborhood collective communication function. So instead of doing sends and receives among neighbor, you can do a neighborhood all gather and so forth. So it can be done more efficiently, and we'll see that as well out here. Okay, so the simplest is you create a Cartesian topology. This is for regular mesh type of communication. So the function for that is MPI cart create. You pass the old communicator. You pass the number of dimensions of this Cartesian topology. That is, if it's a 2-dimensional, 3-dimensional, whatever. Then you pass what are the sizes of those dimensions. So if you're doing 20 processes, is it 10 by 2 or is it 5 by 4 or what? So that's what you pass the dims. The next parameter is whether this is periodic or not. What that means is if you are on the first row, if the processes that are on the first row of this logical mesh, do they have a neighbor above them or not? So they don't, but is there a wraparound or not? So periodic means there'll be a wraparound and in the other direction. So that's yes or no type of 1 or 0 here. And the next parameter is should MPI reorder the processes or not? That is, if you say no here, that means if you pass 0, there will be no rank reordering. That is, in the new communicator, everyone will have the same ranks as in the old communicator. But the only advantage in that case is you get the other convenience functions for knowing who your neighbors are, and we'll see what those functions are. There is no performance improvement because the reordering has not happened. So in general, but you don't need to move the data either. So if you have generated data and you don't want to move it around, don't reorder here and get the convenience of the Cartesian. The other convenience is that we will see. But in general, you want to pass reorder equal to 1, so yes, reorder. Even then, the MPI implementation is not required to reorder. You're saying, okay, if you can reorder, reorder. And what you get back is another communicator which has this Cartesian topology sort of attached to it internally. You don't see it. You can query it. You can get that information. But it's like any other communicator, but the difference is this now has this Cartesian topology information on it, and you can do some querying, and we will see what those query functions are. So let's look at an example. So suppose you have a 3D, you're running a job on 25 processes arranged as a 3D mesh logically because you have a 3D domain regular grid that you want to divide in all 3 dimensions. So you have a 5 by, this is 125. So you have 125 processes and arranged as 5 by 5 by 5 logical grid. You have set the periodic in all 3 dimensions. That is just for the query function. So when the top row asks who is my neighbor above, the answer will be the one right at the bottom, and so forth. So you filled in these things, and you call MPI cart create with the input communicator, which could be MPI com world or something else. The number of dimensions is 3. This is the array of dimensions. This is the array of periods. Note that some of them could be 1, some could be 0. So all that flexibility. You won't need to do that, but that flexibility is there. And this says don't reorder. So you could pass 0 or 1. I encourage passing 1 here so that the reordering happens. And then you get a new communicator. So this is the topology aware communicator, or whatever you call it. It's a communicator with the topology information embedded on it. So you've got a Cartesian topology now. One question is, when you launch a job, you're just specifying one number, right? You say launch this on 2000 or whatever. How do you know how to arrange the 3D, the numbers in the 3D? So let's say you're doing a simpler case. Let's say you are launching on 100 processes. How do you know whether 10 by 10 is a good decomposition, or 20 by 5 is good, or 25 by 4 or whatever? In general, it's hard to know. So there is a convenience function provided. If you know for what you want to do, you can just use it, or you can ask MPI to suggest. So before calling this cart create function, you can ask MPI to suggest. So you can say you can call this function MPI dims create. You say for so many nodes, so let's say 100 nodes and 2 dimensions. Return this array with the suggested decomposition. So the MPI would fill this dims array with 10 and 10 typically, because it will try to do a balanced decomposition. And there is, you can even specify one dimension that you know the size, and it will try to fill the other one. So this array, if some of its sizes are non-zero, MPI will maintain that size, and it will fill only the other sizes and so forth. So those kinds of flexibilities there. Yeah.
You can use MPI with parameters, right?
Yes.
Yeah.
Yeah.
I have a question.
Yeah.
You said that we only have to use we have always to specify the dimensions, but as far as I know, the topology the topology of this hardware is kind of different from this Cartesian, right? For example, in BlueJean, in Mira, for example, we have the actual topology of the hardware is different from this topology.
Yeah, so this topology is more of a logical topology that matches your problem. So if you're operating on a 3D grid, right? Your problem is a 3D grid, and then you want to partition it in all 3 dimensions. So you'll have a virtual process topology of a 3D grid. How that is mapped onto the BlueJean hardware is up to the BlueJean MPI implementation to do the mapping.
Okay, so we cannot actually utilize. So the user cannot,
Because tomorrow, today you're running on BlueJean, tomorrow you're running on some other system, right? Your code as such will not change. You will still have your 3D grid of processes, and the MPI implementation on both systems should do the right mapping. Okay, so this is just a convenience that you can call before calling cart create. So this is an example of how you use it. So you're running this program for any number of processes, that is P. You get the number of processes, MPI com size. Then you call MPI dims create. I mean, that's the previous function. You pass P, and you pass 3 as the number of dimensions, and you pass this array, which MPI will fill out for you. And it will try to divide this P into the 3 dimensions in a balanced way as possible, so that you have a good decomposition. If you do it in an unbalanced way, that the communication volume is not good typically. So if it's 100, then a 10 by 10 results in more balanced decomposition rather than 50 by 2 or something. That's not. So MPI can suggest a good number. That's one, and there are other convenience functions. So yeah, so this is not a convenience, this is a query function. That is, the convenience functions will come later. So suppose you're given a communicator with a topology attached to it, how do you know how many dimensions were there? So this is more useful for libraries, I would say, because the user passes the communicator to the library. How does the library know what was attached to it? So you can get the dimensions of the Cartesian topology, the sizes, and these functions are useful in user code as well. The translate coordinates in the Cartesian topology to rank of the process, and the other one is to translate rank to coordinates. So, I am rank 1. What is my position in this 2D or 3D grid of processes that I've created? So if you didn't use these functions, you had to do all that calculation to know where am I exactly located. And conversely, given coordinates in that 2D grid, what is the rank of the process? MPI can give you that directly with these cart rank and cart coords functions. And the other useful functions are to know who your neighbors are. So this function tells you can find out in any dimension who is my neighbor. So if you want to know who is my neighbor, the top, down, left, right, you can even find the neighbor, not immediate neighbor, but you can with a skip. So not your first neighbor, but that neighbor's neighbor also you can find, and that is it's this displacement function. So you pass the communicator that has a Cartesian topology attached to it. The direction is just whether it's the dimension number 0, 1, or 2, whichever direction you want to go. So it's for a 3D, it's 0, 1, 2. It's the direction in the grid. The displacement tells you whether it's the nearest neighbor or at a distance of 2 or a distance of 3. So there is that flexibility also. You can find pretty much anyone in the grid that way. And what is the source and what is the destination? So you don't have to find out even for yourself. You can find who your neighbor's neighbor is, because then you pass the source as your neighbor's rank, and who is that neighbor's neighbor in any dimension. So you could do this calculation yourself if this was not available. It's just tedious. So these are convenience functions.